Hello! Today I'm going to do something a little different. Those of you who saw my previous video saw that I did acquire a new telescope, and when I acquired it the electronics were not working, and so I'm going to simulate the sophisticated troubleshooting process I went through to fix this telescope and turn what was actually, I got a very good bargain on it. I'm surprised at how inexpensively these used telescopes are going for, especially when the electronics aren't working. I paid about what it was worth, but since I was able to repair it for practically nothing, I've turned it into a nearly new condition telescope that's worth at least 4 to 6 times what I paid for it. Of course, I have no intention of selling it, but we're going to talk about what I did to repair it, which turned out to be a very simple repair. The troubleshooting process of using up fuses in the process of troubleshooting was a lot more than the troubleshooting process itself. You'll see it's quite simple. But before we do, let's take another look at the telescope just to tell you what I've got here. This is a, let's see, is the name there? There it is. It's upside down, of course. Here we have a Meade LX200 EMC. This is the classic Meade telescope. I think they were selling them starting in the early 1990s. I have no idea how old this one is, 25 to 35 years old. And it's in excellent condition optically. I still have some cleaning to do, but as far as the optics are concerned, it's in excellent condition. Let me pull this lens cover off here so you can see what it looks like. So this is a Schmidt-Cassegrain telescope, says so right there. And in my video about optics, that's kind of disturbing, isn't it? In my video about optics, I talked about what a Schmidt-Cassegrain is, but just a quick explanation. This telescope has I think it's an 11-inch diameter mirror. It's going to be a little bit bigger than the corrector plate on the front, which is typical for Schmidt telescopes. And the way it works is that it has a spherical mirror, meaning that the mirror is part of a huge sphere which has a curvature. Well, it's going to, center of curvature would be just about twice the distance from the mirror to my finger. So that sphere would have a radius of my finger still, yeah, my finger's still in the field. So if we take the size of the telescope here from there to there and quadruple it, that's about the size of the sphere that mirror would be part of if it was a complete sphere. And the problem with a spherical mirror is if they have a focal length shorter than about 8 times the diameter of the mirror, the problem of spherical aberration becomes big enough that it's a problem. Spherical aberration means that the edge of the mirror focuses closer than the middle of the mirror. So you have a range of focus. So you can't really get properly focused. If the mirror is shallow enough that its focal length is at least 8 times the diameter of the mirror, it's doable. So you'll find that most telescopes that have a spherical mirror are going to be about 8 times the diameter of the mirror in length. Well, as you can see, this is much shorter than 8 times the diameter of the mirror. And so they have fixed that with a lens in the front, this big 10-inch diameter lens, which has a rather strange shape, looks something about like this. I found out that the Meades have a curve on both sides. You can't see the curve. I'm looking at it. I'm looking at a reflection off of it. I can see a little bit of movement of the reflection as I move the scope, but I can't really see a hint of the curve. So it's very, very subtle. But what it does is it takes light coming in at the edge and it makes it go outward a little bit. Therefore, that makes the edge focus a little longer. And also it makes the light that goes toward the middle go inward a little bit, causing the inner part to focus closer, and compensates so that instead of the edge focusing closer than the middle, it compensates and brings all of the light rays together to focus in one place. The classic Schmidt, the original Schmidt telescopes were really strictly cameras, meaning that the light simply focused onto a film holder and they would use that to take pictures. And the original Schmidts had the corrector plate at the center of curvature. So a classic Schmidt camera, if I had one this size, the corrector plate would actually be way out here. But this one is made to work as it does. This is a Schmidt-Cassegrain, Cassegrain meaning that we have a system where the main mirror, instead of focusing to some point, and this one would probably focus somewhere right around here, I think, we have a second mirror that is curved outward. In this case, I'm trying to remember the one where you would put the mirror further out and have it curved inward or concave. This is a convex lens, and I believe it's spherical, at least in this particular design. And that acts as a diverging lens. So that light comes to the secondary mirror and it bounces it back through a hole in the primary. Now, if it was a flat mirror, that light would just, hit the mirror right about here and then focus, right about there. So this would focus right about here without the secondary mirror in the way. And so if we just had a flat mirror there, of course, it would just focus somewhere around here. So that mirror is convex, acting as a negative lens or a diverging lens. And so instead of focusing here, it diverges the light out so it focuses roughly right about here. I don't have my eyepieces on here. There's a little holder that goes here for the eyepieces, and I also have what's called a star diagonal, which is just a flat mirror that bends at a right angle, so it's a little easier to look through. But anyway, that diverging lens makes it focus longer and eventually focuses here. And so what I have with the combination of the optics is a telescope whose focal length is effectively 10 times the diameter of the telescope. It tells me this stuff here. It says that it is there it goes. It says F10 right here. So it says Schmidt-Cassegrain F10. F10 means that the focal length is 10 times the diameter of the optics. And so instead of a lens, we have a mirror, of course, and I explained how they work the same in my video on optics that you can see linked in the description below there. So this is a 10-inch, so that has a diameter of 254 millimeters, so about 250 millimeter diameter. And so after going through the optics, it's magnifies to the same amount as a telescope that were 2,500, in fact, here's the focal length, 2,500 millimeters. So obviously this is not 2,500 millimeters, which is a little over 8 feet long, but it acts as if it were over 8 feet long. So that's what I have in this little compact telescope. The disadvantage of that is that I get a pretty narrow field of view. So the longer your focal length, the more power and the more a telescope magnifies things. And this one magnifies quite a bit with this long focal length. And so looking at deep sky objects, it depends on the object. I haven't had much of a chance to really use this because of the weather, but the other night I looked at the Pleiades, which is a small star cluster. If you go out in the fall and you look up in the sky around 10 o'clock at night when it's high in the sky, you look up and say, oh, there's the Little Dipper, because there's a little asterism up there, a little mini constellation, if you will, that looks like a Little Dipper. Well, that's not the Little Dipper, that is the Pleiades. It's a star cluster in the constellation Taurus. The Little Dipper is actually much bigger than the Pleiades and much fainter too. I cannot fit that whole star cluster in my field with my longest eyepiece. So the longer the focal length of the eyepiece, the less power, and the longer the focal length of the main assembly, the more power. So to find out exactly what your power is, you divide the focal length of the main mirror with the focal length of the eyepiece, and you get the amount of magnification, which I haven't actually calculated, but I had a 42 millimeter eyepiece, so it's a pretty long eyepiece, and I couldn't fit the whole Pleiades in there. So this is a pretty powerful telescope, so it's not good for really wide angle views, but that's not what it's made for. If I want really wide angle views, I'll get a differently designed telescope. So here's what fell into my possession, and that's the basics of the optics. And just to say a little more, your typical simpler telescope would be a Newtonian, where the light is going to focus onto a flat mirror that's diagonal. So here comes the light, hits the diagonal and goes out the side where the eyepiece is out on the side. So if you see a telescope like this one where the eyepiece is at the front end and off to the side, that is a Newtonian, obviously named after Isaac Newton. And they do make Schmidt-Newtonians. They're kind of rare. I don't think you'd buy one commercially made, but there are still a few amateur telescope makers. Making optics is not an incredibly difficult process. and there are amateurs who will make Schmidt-Newtonian. So in other words, you have the corrector plate, the spherical mirror, and then a diagonal here that would send the light off to the side, but that's not exactly common. Most telescopes today are commercially made, but when I got into astronomy, most telescopes were made by amateurs. So you saw all sorts of designs. I could stand here all day and just talk about different telescope designs. So this is a Schmidt-Cassegrain, meaning that the light reflects back through the mirror. So we have a mirror here. Actually, we have a corrector here, mirror here, secondary mirror, and the eyepiece goes in the back. So the light path is to the primary mirror, to the secondary mirror, and then back through the primary mirror, and the eyepiece goes back here. So anyway, that's the gist of this telescope. This, of course, is just a spotter scope that you use to line up the main scope. And now I'm going to get into the electronics because that's what we're here to talk about. So this is not something I'm crazy about. This is what's called a go-to scope, meaning that you can push in numbers. Where's the control paddle? Right here. Here we have the control console. And it takes a very short time to learn how to use this. And if I want to see an object, assuming this telescope is properly aligned with the Earth and everything, which is a fairly easy process, I can, let's say I want to look at the Orion Nebula, which is one of the few things you can see right now because of the seeing has been terrible the last few weeks. But I know that that is Messier number 42. Messier was an astronomer, Charles Messier, who in the 1700s made a catalog of things not to bother looking at because he was looking for comets. And what's a comet? It looks like a fuzzy star. So he found all the things that look like fuzzy stars in the sky and a few things that you think, why did he think that looked like a fuzzy star? Anyway, he cataloged them and cataloged 110 of them. And number 42 is the Orion Nebula. So I would just press M42, enter, go to, and the scope is going to go right up to it, and I can see it, and oh, look, there's a fuzzy star. I'm not crazy about that, except when I take this to public star parties, which I'm going to do a lot, where I'm showing things off to the general public. It's going to make things a lot easier to find than the way I'm used to doing it, which is knowing where it is, being able to point the telescope there, line it up, and get in there, and it takes a little bit of skill to do that. Today, everything's a go-to scope these days. And with a 10-inch scope like this, it's not so much an exercise in futility, but people are buying like 5-inch go-to telescopes, especially non-astronomers. And they'll buy a go-to telescope, and I'm not even sure if they can figure out how to align it properly, but maybe they can when they're new to this. And so they get it lined up and they say, okay, let's look at this object. And the telescope slews over to it, stops, you look, oh yeah, a fuzzy star. Okay, let's look at the next object. Mention the numbers, slews over, stops, looking at, oh, okay, now another fuzzy star. Okay, let's slew over to the next one, and goes on over, and yep, there we go, another fuzzy star. So, that's not going to be too exciting to the newbie because you're going to see nothing but fuzzy stars in a really small telescope. So I say learn the sky, learn where things are, learn how to point it yourself. And then when you find that fuzzy star, that's your fuzzy star. Look at that. I'm looking at the Orion Nebula. It looks like a fuzzy star, but I found it. I know where it is, and I was able to point at it. On the other hand, this larger telescope does give a pretty good view of things, and the Orion Nebula, even in the terrible seeing in my area for the last few weeks, can look spectacular in a scope with a large light gather like this one. So maybe it's not such an exercise in futility, but how many people new to the hobby are going to buy a telescope this big? Some people with more dollars than cents might, but the average person is probably not going to be able to afford something like this. I'm very lucky I found this thing dirt cheap. I stole this telescope literally, and I would not have bought it otherwise. I've never intended to own a big telescope because I have access to big telescopes anyway. The local astronomy club has a 22-inch diameter telescope that I can go use virtually anytime. Not anytime I feel like it, but I've used it many times, because it's there available to use as long as the person who's trained to operate it is there to keep an eye on me. I can go there and wait my turn and look at whatever's in the sky with that, or even, I've never taken pictures with it, but I could if I wanted to. Now I can do whatever I want, basically. So I never intended to own a telescope because I had access to big telescopes, but this fell in my lap at such a price, I had to buy it, so there it is. You can see here that there's a calibrated ring here that's called a setting circle, and this is for declination. Declination is for north and south. It's analogous to latitude. In fact, if you are standing at 45 degrees north latitude and look straight up, you're looking at 45 degrees north declination. So that's just corresponds to latitude, and it's pointed at 0 here because it's not mounted properly to look at declination. So it's looking at 0 degrees altitude. Over here I have another one, and this is a right ascension setting circle. It's calibrated in hours, and as you can see, I can move it around because how this is set up on the telescope depends on what time of year it is, what time of day it is. And so this has to be set each individual observing session, and it measures in hours because the corresponding measurement to longitude is called right ascension, and it's measured in hours, and 1 hour is 15 degrees, and so there's 24 hours around the circle. So this is calibrated in 24 hours, each hour being 15 degrees, which gives me a bit of a problem using it in an altazimuth mode, altitude and azimuth mode, as it is now. This works fine to find altitude. If I can find the altitude of an object, I can use this and get pretty dang close to it. But as far as azimuth is concerned, well, my so-called azimuth ring is calculated in hours, and I have to remember, okay, each hour is 15 degrees, a little harder to use. But that's intended to have the telescope mount tilted to the angle corresponding to my latitude, so that the axis here, so that this axis, the equatorial axis, is parallel to the Earth's axis. And then I only need one motor to make this follow objects in the sky, because as the sky turns, I can have a motor that turns this in the same direction and follow that object, assuming that this is tilted. I need what's called an equatorial wedge to make that work, and I bought one, but it turned out to be the wrong one. It will fit, but it's not made for this 70-pound telescope. It's made for a lighter one, so I haven't figured out if I'm going to return it or try to beef it up or sell it or whatever. But anyway, that would tilt this so that I would have the equatorial axis. Here's a picture of a telescope on that axis, and that's how I'm used to using telescopes, in which case this now becomes hours, and once calibrated, I can find an object by knowing its right ascension and declination. But I never use setting circles because I find where an object is. I say, okay, it's right, let's see, there's Deneb, and I go down Deneb and look for that little star with the little curve of stars next to it. That's the constellation Vulpecula. And then right next to there, right there, and then I can say, okay, it should be right there. And I can point my telescope right where it is and get it in there and find it myself. Never used setting circles before. But now I have the electronics. All I have to do is punch in M27, and there's the dumbbell nebula, which I was just describing how to find that a moment ago. So anyway, without further ado, let's start taking a look at the electronics here. So I'm going to move my camera and get a closer look at what I'm doing down here. So let's move on over. And here we have the control panel here where everything plugs in. So let's tell what happened when I first got it. I tried it out, of course, and nothing happened. So anyway, just going to show how things plug in here. The little keypad plugs in here. We have a second cable here. Looks like any old telephone cable or something, except it's got RJ45s like Ethernet. And this plugs into there and to there. So this runs the declination motor. And so let's get these out of the way for the time being. And so I, of course, plugged in the power and turned it on. Nothing happened. So I needed to get in there and find out what could be the problem. So I had been told that I could expect that probably a voltage regulator in this panel here had died. So let's open that up real quickly. Take a look at what we're looking at there. Need someplace to put these screws so I don't lose them. Here we go. As long as I don't knock this plate off the table, I'm good to go here. I'll put those over here where I won't knock them off the table or something. And so let's see if we can get this off here. And something is holding it. So there's a little ribbon cable right here. So let's see if we can pop off that ribbon cable without bending any pins on the header. Rock it off a little bit at a time. There we go. So here is the control panel, and we flip it over, and big capacitor there. Probably should replace that battery. Who knows how old it is. But that capacitor is across the power input, and if you notice here it says 18 volts. And if you look right in here, we can see that there is a little 3-pin regulator, and there are the obligatory capacitors next to it. And I need to replace those, or at least one of them, as I will mention in a moment. But I found that this fuse here was blown, so I replaced it with a 5-amp fuse and tried to power it on, and that fuse blew immediately. So I'm down 2 fuses. So now what I'm going to do is figure out what's wrong. There must be a dead short somewhere if that fuse is blowing. So let's get this thing around and flip it down to put this in the proper position here. Lock the declination axis. And I'm going to put the lens cap back on. And now comes the fun part. I need to spin this whole thing around. This thing weighs 75 pounds. Oops, I need to lock my right ascension axis here. Okay, here goes nothing. 75 pounds. At least that's what I've been told. I haven't weighed it, but I've been told it weighs 75 pounds. Let me go around the other side where I can lay this down without killing myself. Get those out of the way. Okay. Now I'm going to spin this around so I can have hold on the handles. Lock that declination axis. Oh, do I got to take this guy spotter scope off first? I'm going to break that. So there, spotter scope is off. Let's put that somewhere convenient. Now let's lay this down. Okay, here we go. Ooh. Yep. Glad I had that cardboard there. I hope it didn't knock anything out of alignment. So what do we have? Oh, we have nothing because I never put those screws back in. So anyway, there's 1, 2, 3, 4 screws I needed to remove there. I looked up to make sure whether I needed to remove those or not. No, those are holding an IC in place. So I just need to take these screws off, which of course are Allen screws. So let's see, where's my, find the right size. They're loose enough. They should not be that loose. I should need to tighten those up a little better. So off that comes. Off that comes. Those are holding this to this is acting as a heat sink for a circuit. So I needed to put those screws on there. And of course, I need a small screwdriver or something to reach in there. Okay, here we go. So there's the bottom. As you can see, there's a couple of, actually those, yeah, they're some kind of an IC. They go to this little heat spreader here and onto there, and you can see the heat sink compound. So I want to make sure those are connected properly. So anyway, here we are looking at the insides of this. Now, if there was something seriously wrong with the computer circuitry, I'd be dead in the water. I wouldn't even know how to troubleshoot that. I'd probably just have to replace the board, which they do make aftermarket boards. Meade, of course, went out of business just a couple of months ago, and so I cannot get replacement parts from the factory, but people are building replacement parts. And there's a little bit of a kludgy thing there, some diodes just kind of hanging out. Same kind of thing here, a capacitor, so a little bit of reworking of the board there. That is often done in new things. That's nothing new. Doesn't mean that there's been some repair work done on it. And in fact, I don't think there has been any repair work done on this, but now let's zoom in on the offending part if we can. Let's see. Are you going to focus for me? Yes, you are. Do we have it? Do you take a look? Let's see. Focus, focus, focus. Are we going to focus? Yeah, I think, is that focused? Look what we've got right there. Sticking out like a sore thumb, a little tantalum capacitor that is a little bit brown and has a little piece of it missing. Gee, could that be the problem? So I unplugged it, took out my ohm meter and put my ohm meter across it, and then, well, there could be a short circuit somewhere else, but it was definitely a short circuit. Now, where is that tantalum capacitor? Well, if we see, are we in focus or not? Well, whether we're in focus or not, we'll have to deal with what we've got. But that is a little 3-terminal regulator. This is just a little linear power supply. We built one as a project earlier in the course, just to learn how to put components together to make a bigger circuit, because it's hardly worth making a linear power supply when for a couple of bucks you can buy one of these, the whole thing in a chip. But here's the basic circuit of what this is. Of course, this is a little more sophisticated, but it's nothing more than a linear regulator. And it's got 2 capacitors, one on the input and one on the output. These are basically decoupling capacitors to smooth out any voltage transients, and also possibly to prevent that from oscillating. It's theoretically possible they can start oscillating, and these decoupling capacitors can prevent that. They are not critical to the operation of the circuit. So all I did, as you can see, this is still there. I just took my flush cutters and clipped one of the legs, and then I plugged everything together. I'm not going to do that right now, but this is hanging here. I plugged that into there. I didn't have any 2-amp fuses, so I put another 5-amp fuse there and plugged it in, turned it on, and it started working just like that. Little $2 or cheaper tantalum capacitor is all the problem was here. So I had it working, except I didn't, because after I got it going, I heard a loud bang. Couldn't tell where it came from, but I said that wasn't good, and it stopped working again. Well, to make a long story short, I checked out my little power supply right here that came with it, and it was dead. And this turns out, I'm not going to open it up again, because I've completely repaired it, but it turns out it's just a simple unregulated power supply. So we look back at our regulated power supply, we have a transformer, rectifier diodes, and a capacitor. That's all that's in here, and a fuse. It had a 5-amp fuse in there, which blew. So something caused it to go bad again. I heard that bang when I plugged in, can you see where I'm pointing here? Where the declination motor plugs in with this cord here. And that's when I heard the bang. And said, let's take a look at that declination motor. So now this is going to be a little tricky. I'm going to zoom this back here. But I'm going to have to move my camera. So let's move the camera over to here. I don't know how good the lighting is going to be. But there we are. And I'm going to have to remove the declination clutch lock here. And here is the declination motor setup. It's just a little DC motor. In fact, the main motor is a DC motor. But anyway, if you look right here, let's see if we can zoom in on that a little bit. Some obvious stuff going on. You can definitely see some black goodness right here. And if you look real carefully, let's see if I can move the camera around to the right place. I can't really get it focused and the lighting's bad. So right here we can see another regular transistor package. It has yet another 3-terminal 5-volt regulator and another tantalum capacitor. It popped. I replaced it with this regular electrolytic here. That's only a 16 volt capacitor. The tantalum capacitors that are blowing are 25 volts, and I put a 16 volt there, but I'm going to replace it real soon with a 35 volt tantalum capacitor, or is it a 50 volt? A much heftier voltage tantalum capacitor. And so that's what blew the second time, and it seems like these tantalum capacitors blow too short. So I replaced it and replaced the fuse, and voila. So we come back around over here. It is now working again. So it turns out that the internet says, so I zoom that back out there so we can see what we're looking at, that there are 4 of these tantalum capacitors that tend to blow on these older Meades. This one here, the one on the declination motor I just showed you, and there is another one in this package here. If I spin that around, there's one in here too that next to this regulator. Yeah, you can see what I'm pointing at there, that tends to blow, and there's another regulator with a capacitor inside the handset that tends to blow. And according to the internet, if the one in the handset blows, it tends to blow this ribbon cable. So I need to replace that forthwith, except I made a slight change. Once again, this is the 18 volt power supply that came with the telescope, but the recommendation is to simply run the telescope on 12 volts. Well, I tried that, and I didn't like the way it was acting. It was kind of felt to be straining a little bit. And also, we have right here a little current meter. So it's a little linear meter, so each one of these segments, when it lights up, is another 100 milliamps. And for some reason, running on 12 volts, this would go up to about 700 milliamps, and then 800, and then 900, just kept slowly creeping up. I don't know what could cause that, but I didn't like it. So I happened to find this 14 volt power supply, and it's a little 14 volt unregulated power supply. It's got a cigarette lighter plug here, so it's obviously made to simulate a car battery for things that originally were made to plug into a car. And it actually puts out 14 volts. I forgot to say that I tested this 18 volt power supply, and it actually puts out 21 volts, getting pretty close to that 25 volts that those capacitors can handle. And they should be able to handle it, but apparently they're not. And so the recommendation is to go down to 12 volts. I'm running on 14. But when I'm in the field, I'm actually going to, in fact, even at home, I'm going to run this off of a power bank anyway, a big Blue Eddy power bank that gives me 12 volts. I can charge that up, and I don't have to worry about plugging it in. It'll run all night on one charge, I think, from what I saw. So that's only 12 volts anyway. And so I just adapted this system here to a cigarette lighter. So just plug the cigarette lighter plug into the Blue Eddy, over into this, and just run it on 12 volts. So I haven't shown you any of my actual repairs. I don't want to take the time to do that. But it's just a matter of removing these tantalum capacitors and replacing them. I've ordered replacements that are either 35 or 50 volts, I forgot. But replacing those 4 capacitors, make sure they don't blow again. Took out the 5 amp fuse here and replaced it with a 2 amp fuse, and everything's the way it should be. Even as it is now, without this capacitor, once again, this is clipped out. It's not actually in the circuit. It's working just fine, but I'm going to replace them. And after doing that, I have essentially a like new telescope worth at least 4, possibly 6, or maybe even 8 times what I paid for it. It depends on the accessories. So there you have it. Had I not been able to repair the electronics, I had already taken it apart and counted the teeth on the gears. You can't really see it there. There's a big worm gear that goes around here, and there's a little DC motor here. I don't think you can see it, but there's a little DC motor, and the electronics control that and turn the worm that drives the worm gear. And I counted the teeth and determined I needed an 8 RPM motor to just drive that at the right speed like I'm used to. Not used to all this computer control anyway. But then I fixed it. So I have a perfectly good Meade 10-inch telescope here. So there's my sophisticated troubleshooting. Found black parts. Probably one of the important things to know here is I knew that that was not a critical part, and I simply clipped it out of the circuit, and it started working just for testing purposes, and I will replace it. So there's my experience troubleshooting this sophisticated electronics here. Just replaced some blown capacitors and got this working, and now it's like new. So I hope you found it useful and informative. If you did, please don't forget to give me a thumbs up down below. Helps other people find these videos, helps the channel. And if you'd like to help me make these videos, you can go to patreon.com/Vocademy and pledge your support. If you can't support me monetarily, remember that subscribing to this channel helps other people find it, and that's a big help also. So a big thank you to my patrons at Patreon who make this possible, and to my one-time donors also. And a big thanks to everyone for watching.